8.1, Pythagorean Theorem.
Exactly on time.
All right. So this first part, I think we could. Well, I think everybody knows this part. So we're going to say for any right triangle, doesn't matter what kind of right triangle. Right triangle, what does that tell us about the triangle?
90 degree.
Has a 90-degree angle. So for any right triangle with sides length A and B and hypotenuse C, what do we know? You probably got this word right. So what is it? A squared plus B squared equals C squared. Probably the most famous equation in math. One of the most important equations in math. Probably in the top 5, maybe in the top 3. But it's debatable. It comes up in a lot of different places, a lot of different contexts. But it's really, really, really important. So hypotenuse. Let's draw a picture. So here's my right triangle. Hypotenuse, there's my 90-degree. Which side's the hypotenuse? The longest side. Good. So the hypotenuse is the longest side, so that's going to be C. And what's another way? What's another way we can think about finding the hypotenuse? It's across from the 90-degree angle.
The hypotenuse, sure.
Right, the hypotenuse. Mrs. Voss has a hippopotamus shirt. And the other two sides, it doesn't matter which one we call A and which one we call B. We can switch those around, but the hypotenuse always has to be the longest side, so A squared plus B squared equals C squared. It's called the Pythagorean Theorem. People have known about the Pythagorean Theorem since Babylonian times, 1700 BC. They found clay tablets that have numbers that work in the Pythagorean Theorem written on the tablets, so they knew about it. It's been an important equation in terms of math, and it's also an important equation really for the development of civilization, because they used it for architecture and agriculture and that kind of thing. All right, so I just want to do a couple of examples calculating with the Pythagorean theorem, and then we're going to add a little bit of information. So we'll do an easy one first. So there's my triangle. I'm going to say 8, 15, and question mark. We'll call it x. And the problem says find x. So it can be helpful to make sure you set everything up right, just to label your sides. So which side is the hypotenuse? Which side is C? X. So that's C. The other two, it doesn't matter which one we call A and B, so I'll just call that A and that one B. And then we just plug our things in the right place in the Pythagorean theorem. So I can say 8 squared plus 15 squared equals x squared. So we get 64 plus 225 equals x squared. Add these together, so x squared equals 289. And how do we undo a square? Square root, take the square root, both sides, and x equals, anybody know the square root of 289? It's a perfect square. Almost. 17. 169, 13? So the 9, you're on the right track. All right, so there's that one. Questions there? Let's do one that we have to we have to be a little more careful with, and I want then to bring back something that we practiced a little bit on, simple radical form. All right, so this one we have x, 10, and 16, and we want to find x. All right, so how are we going to label our sides this time? 16 is C, and it doesn't matter how we label the other two, so let's just do that one A and that one B. So for this one, we're going to say 10 squared plus x squared equals 16 squared. So we're not always going to be solving for the hypotenuse. So I get 100 plus x squared equals 16 squared is 156. So I subtract 100. We have to do a little more work this time. X squared equals, this should be 16 squared is 256. Right. And then we subtract 100, we get 156. So we take the square root of both sides, and this problem is going to say, leave your answer in simple radical form. So we need to simplify square root of 156. So I'll do my little trick that I like to use. 156. What's the smallest prime number that will divide into 156? 2. So 156 divided by 2 is 78. What's the smallest prime number that divides 78? 2. Divide that in half again, and I get 39. And 39 divides into 3 and 13. What we're looking for is pairs. So I leave it until I can't get a pair anymore. So I'm going to just leave that 39 since it doesn't give us a pair. One of the pair comes out, and then whatever's left has to stay inside the square root. So x would be 2 square root 39. And that would be our answer in simple radical form. So some of your questions will ask you to round to the 10th or something like that. But some will ask you to leave your answer in simple radical form. Questions there? Okay. We call 3 whole numbers that work in the Pythagorean theorem Pythagorean triples. So these are just three whole numbers that work in the Pythagorean theorem. A few examples. There's one that comes up a lot. Does anybody know a Pythagorean triple? 3, 4, 5. That one comes up a lot. By the time you get to pre-calculus, you'll know 3, 4, 5 triangle is a right triangle. That's sides of a right triangle. So these would be the 2 legs, and this would be the hypotenuse. A couple of others, 5, 12, 13. 8, 15, 17. Isn't that the one we used over here? 8, 15, 17. So if you remember that was a Pythagorean triple, you wouldn't even have to do the Pythagorean theorem. Another one is 7, 24, 25. These are all right triangles, and these would be the sides, whole numbers that make up the sides of right triangles. And we could also multiply any of these by a whole number. So we could multiply this, the 3, 4, 5 by 2, and we could get a 6, 8, 10 would be a right triangle. Sides of a right triangle. I can multiply this one by 2. 10, 24, 26. Another Pythagorean triple. Sides of a right triangle. So 3, 4, 5 comes up a lot. And the 5, 12, 13 you'll see a lot, especially when you go in pre-calculus when you're doing trigonometry. The 3, 4, 5 and the 5, 12, 13 show up a lot. So it can be helpful to know a couple of those, just so you don't have to do the Pythagorean triple. Oh, that's a Pythagorean triple. The missing side is whatever. But the longest side is always the hypotenuse. All right, we good there? Now we know what a Pythagorean triple means. And these are the kinds of things they found on the clay tablets, is these Pythagorean triples calculated out and kind of written like this. All right, the converse of the Pythagorean theorem. Remember what we do to get a converse of a theorem? We have an if and a then to get the converse. Oh, that was way back in chapter 2. We turn it around and go the opposite direction, basically. Just turn the if and the then around. So our Pythagorean theorem says if we have a right triangle with sides A, B, and C, then a squared plus b squared equals c squared. The converse of the Pythagorean theorem says that if a squared plus b squared equals c squared for a triangle with sides A, B, C, C is the longest, then the triangle is a right triangle. So the converse tells us if we know the sides of a triangle and we know those sides work in the Pythagorean theorem, then we know the triangle is a right triangle. That gives us a way to figure out, if we have the side lengths, figure out whether or not we have a right triangle. That's what the converse of the Pythagorean theorem lets us do. So let's look at an example. So we're going to say triangle with sides .5, 30, and 32.5. Is it a right triangle? So what this question is asking us, anytime we have something to do with the right triangle and the sides of the triangle, what it's asking us is, does a squared plus b squared equal c squared for those sides? So which side are we going to call c here? 32.5. C is always the biggest side. And I can call it, doesn't matter how I label the other two, a and b. So then we try it out. We see, does a squared plus b squared equal c squared? Well, a squared plus b squared is 12.5 squared plus 30 squared. And that equals 156.25. If I calculate that out, plus 900 equals 1056.25. And then I calculate c squared. 32.5 squared. Plug that in my calculator and I calculate, and I see that is 1056.25. and I see that they are the same. So that says, yes, it is a right triangle. Since a squared plus b squared equals c squared works for those sides, it's a right triangle. If this was off at all, if this was 156.24 and this was 156.23, it'd be close to being a right triangle, but it wouldn't be exactly a right triangle. Questions on that example? Well, we can find out even more information about the triangle. If they are not exactly the same, we can figure out what kind of triangle. And we call those the Pythagorean Inequalities. Do you guys remember when we watched Donald in Mathmagic Land, when they talked about the Pythagoreans? They used the pentagram as their secret symbol, and it was a secret. It was almost like a cult. They had really strange beliefs. They didn't eat beans. They had all kinds of things that had to do with being in the Pythagoreans. All right. So for the Pythagorean inequalities, we have triangle ABC, and the sides A, B, and C, and C is the longest side. There are three things we can figure out. If a squared plus b squared, I'm gonna write it the opposite direction. If c squared equals a squared plus b squared, what did we just decide? What does that tell us about the triangle? It's a right triangle. If a squared plus b squared equals c squared, it is a right triangle. The second thing we can figure out, if c squared is greater than a squared plus b squared, it is an obtuse triangle. And the third thing we can figure out is if c squared is less than a squared plus b squared, it is an acute triangle. And this should be a b squared. And the way I think about this is, for a right triangle, if a squared plus b squared equals c squared, we have a right triangle. If c squared is bigger, the hypotenuse is bigger. That makes a triangle obtuse. If c squared is smaller, that makes a triangle acute. So if c squared equals a squared plus b squared, we have a right triangle. C squared is bigger, obtuse, smaller, acute. That's how I think about it. All right, questions on our inequalities? Pretty easy ideas. So the kind of question you might have with these inequalities, it would say classify the triangle. I'm going to just say what kind of triangle. So these are the sides. I'm going to give us the sides of the triangle. 14, 7, and 9. And then I'm going to say 2.5, 6, and 6.5. And for 3, 2, 3, and 3.5. So let's do the first one together, and then we'll figure out what kind of triangle this is, and then I want you guys to work on the other two. All right, so which side is going to be C here? 14. I'm going to call this C. We can call that A and that B. So we do C squared, 14 squared is 196. 7 squared plus 9 squared is 49 plus 81 equals 130. So C squared is larger or smaller than A squared plus B squared? Bigger. C squared larger than A squared plus B squared. So what kind of triangle is this? Obtuse. That's an obtuse triangle. All right, so the other two, I want you guys to work through those. Decide if it's right, acute, or obtuse, and then we'll go over the answers, and then we'll be done. So for number 2, which side is going to be side C? 6.5C, and doesn't matter how we label the other two. And what do we find for number 2? C squared less than, equal, or greater than? Equal to A squared plus B squared. So if we calculate this out, we would say that they are equal, and this tells us what kind of triangle? Right. And finally, for the last one, it's going to be C. Call that one A and B. And what happens here? C squared less than A squared plus B squared. So this triangle is acute. And we just calculate this out and decide, just like we did with this one, how does A squared plus B squared compare to C squared? Questions there? Okay. Homework?
What's the page number?
Page. Just pick a page. 495. Someone was telling me in my other math class that what the way it should work is there should be a math problem that you have to calculate to tell you the page number. So if you do the problem wrong, you do the wrong problems. I was a little upset because I didn't think about it. Yes, Harry.
When you give us homework, you give us problems based on
How talkative I was?
like, you know, like if we were talking over you, you give us more problems.
No. That's another good idea. All right, and but before we're done, since we have a few minutes, I want to show you this little thing that has to do with the Pythagorean Theorem. Kind of nice. So one way to prove that the Pythagorean Theorem works, one way to think about it is if you look at this right triangle, if you make a square on the side of the hypotenuse, the area of that square, it's C squared, C times C. So C squared is the area of that square, A squared is the area of that square, and B squared is the area of that square. So you can add the areas together, and it equals the area of the big square. And then what's happened here is on the green squares, we've drawn another right triangle, and then made squares on the sides of that right triangle. And we're going to do that process again, make another triangle and more squares. So let me do this. So there's the next step. And then we can do it again on the little squares here. And you get a nice tree that's based on the Pythagorean Theorem. And it turns out that this is a fractal. All of these shapes are copies of this original shape, just put on the other side. They're just smaller. And this, what we'll do next is we'll change the side lengths of the right triangle, and it ends up kind of curving. And you get these nice little kind of spirally shapes. Oh, I think, there we go. And it just keeps adding more and more of the squares and triangles on the sides of the other squares and other triangles. So Pythagorean, that's called the Pythagorean tree or the Pythagoras tree. And it's what's interesting, part of what makes it a fractal is all the shapes are a copy of this original shape, all of the smaller ones, smaller and smaller and smaller. And the perimeter ends up being infinite, but the area stays finite. It's kind of interesting. All right, so there's a nice little side